field of what is known as model editing. So model editing, so maybe the neuromorphic community is interested in what is known as model pruning. So model editing is a more generalized version of this, and we will try to show some instances of this problem and why is it interesting and hard and why is it touches upon modern day problems which AI is facing. So we want to address this problem in what we call as data-free regime. Hopefully by the end of this talk we'll be able to understand, I'll be able to communicate what I mean by those terms. So this a more apt title which we would like to present at other forums is mainly distributional approaches for editing complex models. So what at this point, as the talk goes on, I will say we'll try to throw light on this. But at this point, I would like you to think about this word in complex models. Complex models are not necessarily feed-forward CNNs. And so there are where the ResNets and things like that, right? And modern day transformers. So those are the models of interest, and it looks like editing such models remains open problem and a problem of great interest. So this work is jointly done with a couple of great students. So Chaitanya is a PhD student with us. Dhruv and Tanay both are master students, have graduated. And we gratefully thank AMD and Shell for their generous sponsorship. And now I think, so I don't have to finish all the slides. You're most welcome to interrupt me and ask questions, and that would be a good discussion. Okay, so let's get into the topic of this. Maybe this community doesn't need to know this, but probably it's prophetic in many ways. So here is an article which Cornell University put up on its website to celebrate the modern day progress in AI. And this is the picture of Rosenblatt in, I think, 1950s at Cornell. So as they say very lovingly, that Professor Perceptron paved the way for AI 60 years ago. And now it was indeed prophetic that, as he said, that right, someday this will be able to, this perceptron, which was a very small network then, an idea at best, can perceive, recognize, identify its surroundings. That's his own words. And today we see it reality. But why did it happen? How did it happen? So now you see, this happened because like in this community everybody knows what neurons are, right? Perceptron at that point when he was making those statements was like 10 neurons in a lab, very small things. And now over the years, these things take slow, but over the years, it took some time. Maybe the first probably an effective machine came up in 1988, I believe, like 20,000 neurons, and they were able to understand speech, a reasonable commercial system. I don't know how commercial that was, and things were there. And then maybe around 2010s came our industrial models, AlexNets and things like that. And now, so what I've done is listed down the number of neurons or number of units, if you will, and so now apparently it is predicted that in this year there'll be like in models which are like 100 trillion parameters. So, I mean, we see this power, but this power is coming at this. You add more and more neurons, you find more, it can do many exciting, interesting things, right? And then going back to Rosenblatt's perceptron, it was, as you all know, it was motivated by how the brain works. And when the brain works means the unit of brain is a neuron. And then what they did was they took the McLaughlin model of the neuron. And then things were built as they were. Great. Now, let us, a sobering thought, a human brain has 100 billion connections. So somebody need to think about it. There's also somebody rethink the algorithms as we are doing. So why do we need so many more parameters? Maybe we need to do something more. But that's a different area in itself. However, today's reality is, AI is everywhere, exciting, changing our lives, but number of parameters are quite large. So the problem is, one of the major problems, and this is one of the papers which I saw which really eye-opening for me, and I'm sure many of you have seen this paper. So the carbon footprint of neural network models, right? It is truly alarming. to get a sense of this, so on this side, right, these are names of very famous models, right? And now, like, I think what the authors did is that they took these models and checked that if you go to state-of-the-art conferences like NACL and SAML and things like that, and say how many iterations they were training these algorithms for, and they could in some way compute energy consumption number, right? These energy consumption numbers. And now you can, for energy consumption, for every energy consumption number, you can also associate a carbon footprint of it. So this is called CO2e. E is equivalent, carbon dioxide equivalent. And these numbers are available for in many countries. For example, these numbers are for United States. So if you can tell me energy consumption, I can tell you what is the CO2 equivalent is. Okay, these are some numbers, but let's contextualize these numbers. Now you see, if you travel a passenger trip from New York to San Francisco and back, your CO2 equivalent is 1984, right? Now look at one iteration of BERT, 1907. For example, a car in its own lifetime, is something like, this is the number, like 1,26,000 CO2 equivalent pounds. Now, if you take a transformer, a reasonable size transformer, now this is small, 213 million, right? Now look at the power consumption, CO2 equivalent consumption, 5 times that. Now all of us want our transformers, all of us want our models. So this is going to be clearly going to be unsustainable, and that's what is anyway happening. On a lighter note, when we push our students as a conference, you should do compute and all that, and they sometimes say, sir, the GPUs are there, the room feels heated. I say it lightly, but this is a serious concern. How can this be a technology which we are banking upon to take us to the next level with this kind of carbon footprint? And of course, that's why this neuromorphic community is the community who's thinking about it deeply and how to build more efficient machines and things like that. So anyway, so that being the point, so now one of the things we have been also thinking is that how do we, what do you do about these things, right? And more details are here in this fantastic paper. I recommend, if you have not read it, I recommend all of you to take a look at this, where first things have been put. Disclaimer, once this paper put out, there was some pushback, obviously from who, the big corporations. But I guess while the numbers may be contested, but I think the scale is not. So maybe you should look this up if you are not already doing this. So now, as you see, the main, so that's the one cost, as you see, carbon footprint, right? So the power of neural network, as can be envisaged, is coming because I'm adding more and more neurons, and my models have more parameters, and they can do wonders. But it comes at a great cost, as the paper puts out. Now, one of the interesting things, and the same paper puts out, is another thing, right? So see, the 40% of the cost, I think, can be attributed to deployment-related costs, right? I mean, so now, for example, so AlexNet came out in 2015 or so, or something like of that order. Now, today we have, I think, Nobel Prize was given to this this protein folding algorithm, right? So now we are living in that era, right? So for example, now it seems in the last 6 to 7 years, or maybe last 10 years, my compute requirement has grown almost like 300,000 times. Large-scale industrial machines, right? So now if you look at if you want to look at a corporate view, this is the NVIDIA's CEO. Like to quote him, he says that at least the industrial deployment is mainly, the energy cost is mainly inference time, not training per se, because you'll train occasionally. All right? So that means, as per the industry requirement, because every time so what is inference here? A simple thing. Every time I call ChatGPT, ask the question that which movie should I go to, ChatGPT, that's inference. All of us use ChatGPT and all that. Every time you pass an inference thing, and some energy is burnt because things running under in the machines. So now he says that the deployment cost, that's something like this: 80 to 90% of the cost in today's machine learning is due to inference. And now we had a similar resonance. So this is Lisa Su, whom we hosted last month. It was amazing. She was here, and she also said the same thing, that see, inference is the market for modern day AI, especially big corporations. So why are we saying this? We are not corporates, we are academics. But I'm saying, so now it is important that AI, to see the full impact of it, this is one sector we must pay attention to. How can I make inference easier, at least computationally cheaper, right? And so basically, then you need to think about it, right? So whatever we do, can I optimize models so that inference times are low and possibly without compromising accuracy? And in this community, I'm sure the neuromorphic community is engaged in building machines which take less energy, and that's a good thing. So we talked about inference. Now let me talk about another problem which is not related to inference but equally important, and that will set the stage up for model editing. And I'm not sure how many of you have seen this news item. This came in, it happened around May. So Scarlett Johansson is a very famous actress, and she's suing OpenAI, saying that the GPT maker, so the GPT models especially imitates her voice. Now, and so this has happened because I think most of the GPT models have been built scraping data from internet. And now when we deploy them, often some people may object to that because you are making financial gains, maybe misrepresenting, because many people may think Scarlett Johansson herself is advocating a product this way or that way. So this is causing a new age problem, right? And now, and how to understand how severe, I do not know, I have not followed up in the story what the judgment was, but I think, so this was a landmark judgment, where I think this is in 2021. So Federal Trade Commission in the United States actually gave a judgment that a particular company which somehow collected data from facial data of human faces and then was building models, and which was commercialized products, and then without the consent of the people whose data was taken. Right now, habit is machine learning models, as we all do, get data from wherever you build models, and then it's it. And that's okay for, I would say, okay for doing laboratory work. And hopefully the models are open, that's what we all do. But the moment we start gaining financial advantage of it, there is a chance that's a very, very, very gray area. And as you can see, the lawsuit and the judgment was that not only have to delete all the data, but also delete all models which are derived from the data. This is a judgment now. So this is throwing up new challenges, because now in this world, the GPT models which we see are very powerful, agreed, but how would the power come from? A, over-parameterization. B, it has been trained on data which is available over the web. And now once you start making money out of it, it is a serious question to ask that, did I consent for that? And that is the place where we are in. So obviously, the field of AI, this is the touch point between AI, ethics, legal systems, and things like that. And that's exciting things are happening there. But one can also think about model editing from this perspective as well to address this issue. So in a nutshell, this sets up this notion of what is called as model unlearning. Hopefully, we'll try to define it a little bit more carefully in the next few slides. But the case in point is that this is an increasingly important area. For example, in Europe, there is this GDPR Act. In India also, we passed this DPDP Act. Soon we will see the ramifications of this. So now, one of the important part of the act is that user can say that I have a right to be forgotten. You should not use any of my data. I want my model to forget things, right? Or even, and legal compliance is demanding, sometimes that maybe you have used proprietary information and hence you should remove this information for this class of people. Scarlett Johansson can go and say that, oh no, please remove all information about me. Now how to do that? It's a model. And the goal is not the data, but the model has somehow learned it. I must tease out that specific information. How do I do these things? So this is throwing up new foundational challenges, and all. My idea of saying this is that pruning and this challenge can all be looked at in a unified framework. That's what we call as model editing. So this talk is based on the following themes, which are various papers appeared in ICLR and EUREPS, and some of them are in review. So basically, we want to solve this problem where we in the data-free regime. And so what is data-free regime? We will be a little bit elaborate on this. So now this discussion came about while we were having conversations with some of the startup companies mainly, who don't have access to, who don't the capability to train things. And just like anybody else around the globe, what they do is somebody puts open source model. Okay, you take the model and you now do something. You have no idea how the model was trained. You don't have the capacity to scrape the internet. So now this is what I call a data-free regime. I given the model, weights and parameters are given. Now you will adjust it. So I don't have access to the original training set. I do not know how it was trained, what loss function, this, that, I have no idea. But now, given this model, I have to do something. So that's what I call a data-free regime, and now we are advocating as what is called the distributional approaches for these things. All right. Okay. So now, So now let's get into this. So to structure the discussion, I thought we will first introduce model editing, a little bit more, put some definitions to it, and then we will show you some results on a structured pruning and model unlearning from that perspective. So now here's the question. Sorry for some math symbols, not necessary, but anyway, to make the talk profound, I thought math symbols would be important. So yeah, so the idea is this: model editing. So it's a model M. It can be many things, right? Now, so here M is your neural network, maybe GPT, whatever. Now there's some reference examples and there's some target examples, right? So now we would like to do the following. The model is behaving in some way. On the reference, it should remain the same. But can you edit the model? Change the model in whatever way you want, so that this behavior on the target example changes. So that means one formulation of this, that Scarlett Johansson, so that the model should behave exactly the same way on any other examples except on Scarlett Johansson. Things like that, right? So this is one way to frame this question, right? Now one might think about it, what is the model now? So what can I change in the model? Editing is changing, right? What can I change? So basically, at a high level, you can change mainly, I guess, maybe broadly speaking, two things: the number of neurons and the associated parameter values. That's all I can do, right? But is it new then? So of course it's not. For example, many of the times we do fine tuning, right? Fine tuning means what? I have trained a model. Now a new set of examples come in, and I want to say, okay, can you adapt the model so that it also works for the new set of examples? This is called fine tuning. Basically, you're changing the parameter weights. This can also thought about as a model editing. Okay. Now the other thing is for transforms, for example, there is notion of adapters, right? So basically, here it's different. You also want to do is that you introduce new neurons, new units, so that I can adapt the neural transformers better, right? But this is the part which has come closest to this community, is weight pruning. That can remove this some of the weights, right? Without sacrificing my accuracy, right? So sacrifice accuracy means now my dr is my dt is the same as dr, right? So all this can be looked at from the same perspective. Now, so now if you want to address the problem of model unlearning, that is that that we talked about earlier, and pruning together, so one can refine the same setup which you are doing and say that, okay, maybe a model consists of components. Now, what is a component is up to you to define. It can be a one neuron, it can be a filter, it can be a group. You decide what a component is and which you can manipulate. Okay? Now, it's kind of filters, attention heads, and so on and so forth, right? Now, the key to doing model editing is I want the output of the model to behave differentially between dt and dr. So then it's critical then to understand what is the behavior of the components of M. So maybe one question I can ask it, how does a subset of components of M affect the predictions? That is, now you draw a subset of components and say, how does this component affect the prediction? Does it predict well, not well, so on and so forth. So that's basically a model editing problem at a very high level. All right. So just to see an interesting state of the art, I think this is a very nice paper which came out this year, CML. So one of the things is that, so basically the ablation is something like removing things, right? So basically these are, let's say, a neural, this is like, say, a neural network, and say that, okay, if I want to remove one of the units, maybe one of the neurons, right? And I see the original thing says a picture, and the picture looks like a cat, right? And then say, so can you now guess, if I remove that neuron, what is the effect of the model? Right, that's one way of thinking about this, right? Now the way they quantify that is that, so for each of the components, let me think about developing an attribute vector W, right? And Vi is the output of the component. That is, now I shown an image. If like as a filter, then there will be a vector of values you can get. Now how does that vector of the values predict that this is a cat, right? So they try to fit a linear regression kind of function, right? And now this W is often computed from the existing dr. I compute W, right? And now use that to now guess, on your target examples what is going to happen. And that's the way so now if maybe one step I should say here, what they do is that they take, for each of these units, they compute this vector W, and then they decide that which of the W's are most sensitive. Maybe if the W value is all small, maybe it's not effective, or W is very large, maybe this is effective, and so on and so forth, right? And they come up with a framework like this. Now, as you see, it is critical for their algorithm is to have access to the whole data set, right? The dr. Now that's what we want to do the same thing in a data-free regime, right? So no access to dr for us. I do not have information of how you have trained it, which data set you have trained in. So that changes the game significantly, right? Also, I don't have information on loss function which you used, right? However, I have access to dt, of course. So why is the second point important? Second point important is that end of the day, what you want is your model should work well on things which you care about. That's why this loss function is important, and most of the algorithms, if you see, are often targeted towards, for example, the previous case, the key idea is now I should be able to propagate the gradient information of the loss is used to find the good attribution vector W. I don't have all of that. So this is in some ways called the zeroth order model editing. Zeroth order means I have no access to, I don't have the derivatives of the things. So here is the setting of the problem. So now this is of course inspired by the previous paper where they coined this term component attribution, but we ask a similar question a little differently. So what components in a neural network? So components are defined. It could be filter, it could be whatever. Contribute most to the predictions. Where contribute is the way you can decide how to position this. Now, can you identify them in a data-free regime? Right, data-free as we talked about. So these are the two questions which we want to, address. So here is in some definitions now. So structured pruning is so removing structures, components rather, not necessarily a single weight, without hampering the accuracy. Okay, but model unlearning. This is probably like maybe common knowledge here, but model unlearning may be new to some of you. So here is a definition for this. So now the definition is this, like the Scarlett-Johansson example, right? So I have a well-trained model which uses a particular image, a particular information. Now, can you build a model without that Scarlett-Johansson's data and produce a new model So in that case, I will say that the model does not have any information about that particular data point. Now, the vanilla way of doing this is very expensive. Then I must start from scratch, retrain everything and things like that. So now the challenge is I have a pre-trained model. I cannot train on the full data set, but I must give you the guarantee that Scarlett-Johansson's data has not been used. That is, I have done something. Now you take your data, take the data where Scarlett-Johansson is removed, retrain, you will get exactly the same model. That's the setting of model unlearning problem. Obviously, it's a very difficult problem, and it's an open issue as well. And maybe you can only approximate it. So we will show you an instance which we call as class-wise forgetting or concept unlearning. So this is what more or less a definition of model unlearning, and as you can see, this will be in the days to come, and it's happening. It will attract many research attention because of the importance of this problem. So now our contribution to that is what we call as discriminative components. So discriminative components are components which are able to discriminate between objects, like say cats and dogs, right? And if you can identify discriminative components, we can identify, let's say there is a component for, so now if there's a neuron, which can reacts the same way as a cat and a dog, right? Versus a neuron which can discriminate, which can say for cat it's very high and dogs it is not, right? The second one has a discriminative ability. So now I have to forget dog. I have to remove that particular unit. So that's the notion of discriminative component, and we will. Okay, so we'll elaborate this in the coming few slides. But this is the mainstay of our thing, and so now to arrive at that, here is a brief summary of challenges, if you will. So by and large, editing is fine, but how and where is most important, right? So now how do you do this? And then the goal is that the figure of merit, whatever you care about, maybe let's say accuracy. Accuracy should not be hampered, or figure of merit shouldn't be hampered. Yet you should be able to edit models efficiently and quickly. So the interesting or the interesting additional factor we bring in is that you don't have access to sort of this training set, which we keep emphasizing. So one more interesting thing is here. We hope to convince you this, right? So model pruning often has this very simplistic notion that okay, more parameters, remove parameters, and model is smaller, and hence you will get gains in energy. This is unfortunately not fully correct. Just because you remove parameters, of course energy will come down. But now suppose I remove 10% of the energy, 10% of the neurons, for a matter of speaking. Would my energy gain come down 10% or a factor of that? No. So that is why it is important to come up with an effect. This is because it is also important. The energy is not only, of course, a function of number of parameters, but it's also how it's engineered. And that's where structured pruning and things like that helps. So unless the full stack is thought about more carefully, it is, we may not see the gains which we wish to see. Okay, so now, so this is one thing we would like to highlight as we go along. So here is like a one slide thing on what structured pruning is, right? So structured pruning is essentially, now if you think of these blocks as like if you think these are like a filters, right? Now structured pruning means you remove each of these blocks together. Whereas unstructured pruning would be, I would remove each of the weights here. So like, for example, I keep this block, but I remove these weights. The white ones are things which are removed, right? Now, you see, if you do this, it is now well known that this often does not give you the energy gains which you seek. Whereas this gives you energy gains because of this, the underlying engineering of it. Well, accuracy-wise, of course, this is better. You have more strict handle, easier to do. But the energy gains, unfortunately, are not that simple. You won't get that compared to structured pruning. But the challenge is to do structured pruning, it's a little bit more complicated than unstructured pruning to get the accuracy numbers which we seek. So here is like a one slide related work. So most methods of structured pruning, what they will do is you take your filter and then look at the parameters and say that the parameter values are small, you throw it away. So this is not very effective in accuracy perspective, right? Gradient-based method, that is, you take your loss and say, okay, if I change this, the sensitivity, how does it affect my loss? Hence accuracy. That's reasonably more effective, but it requires access to gradients. And often this comes also as, using tailored approximations around the loss function at optimality. Now, these are often very, very loose, and also, but more importantly, I can do all this provided I have access to the loss function and derivatives and things like that, right? In other words, for example, especially you want to think about it for your application, that for CNNs, for example, the derivative consists of a backward pass, and that's the most expensive thing. So often these kind of methods will not have the ability to work in a low energy setting, right? So there's other method like reconstruction based methods and all that, right? But often these are, when you start implementing them, you will see that it is sometimes the bounds which they have are non-informative, because of the nature of this problem. And so it's not pretty, and in some sense it's not very useful, I would like to say. More details are there in the paper. Okay, so now let's come back to the problem of discriminative filter. So how do you want to think about it? As you said, we don't have training data set. So now how do I solve this problem? I don't have training data set, right? But you have given some target examples. So what you say is now target concept. You say, look, there's a model you have got from the web, you make it smaller, but I want the model to work for cats and dogs. Okay? Now what I do is I take each filter, whatever filter component I wish. Now I compute the reaction of the filter to the data. That is, I pass images of cat and I look at the numbers which comes out of the filter. I can draw a distribution of this, right? This is like a distribution. Now if I see the distribution on cats and dogs are the same for that filter, maybe that filter is not very effective in discriminating, right? But if the distributions are very different, then that's the thing we want, right? So that's basically the idea, that I have a distributional access, and that's what I mean, right? I have access to the distribution but not to the same data points, right? But then that leaves me this problem that I must be able to measure how much the distributionals are changing. So here is this example, as you say, right? So now suppose the pink filter, right? Now you see the reactions when I show images of cats and dogs are very different. So the brown one is the dog and the blue one is the cat, right? So that's more discriminative. Whereas the green one is not discriminative at all. It's behaving the same way. So now it's probably a rule of thumb can be used that if I throw away the green thing, maybe the discriminative filter ability will still remain. And that's where we can optimize. And that is the core of the idea. Now the question is, how do you measure all of this? And that's where you need a little bit of mathematical formalism. But the idea is that we solve the phenomena. Then I said, okay, let's put a hypothesis. The hypothesis is that if it's a well-trained model, that means you should have a mix of discriminative and non-discriminative filters. When I say mix is very important. So now those of you who know pruning is that the first few layers you cannot prune. Why? See, you also need a representation of the image. So initially there's no discrimination power. So just because it's not discriminating, you should not throw these things away. That's key. They're for a reason. But sometimes they are over-parameterized as well. So now idea is to identify those neurons which are there for over-parameterization purposes and not for representation purposes, right? So that's why it's important to have a mix. And now in the higher layers, there is a significant mix, that the significant fraction are more discriminative, non-discriminative filters, and that's where we see the gains. Now, how do you identify all of this? Now, I think I'm sensing I'm running out of time. So what I'll do is I will, I'll try to go a little fast on this. So one of the good measures of the difference between distributions is sometimes called the TV distance, the total variation distance, right? Now, so total variation distance is that you take an output of a class A and a class B, and now so what you can see is, suppose that I have now many classes. Now for each pair of classes I compute DTV through that formula, let us say, and now I compute the minimum value over all such numbers. So what do I get now? I get the C square. So C classes has C square numbers. Take the minimum value. Now if that value is very high, that means this filter has a very high discriminative ability. If the value is like very low, that means this filter is not that useful. a non-discriminative filter, right? That's where we go about these things, right? Now, okay, this is a very nice formula. So now the question is that, okay, this is very well defined, but the problem is that this is intractable, as all nice things in life, right? So when you come to a nice formula, but then you can't compute these things. Okay, so now there is, so what we do is, okay, we boldly go and make assumptions and assume it's Gaussian, which is of course not right. So now, why Gaussian now? To Gaussian things, we can come up with reasonable proxies. And one of the proxies I think is a lower bound on the DTV. Now you see, you want DTV to as low as possible. So if I can prove a lower bound is high, it does the job, right? So that's where we use now. And now, though we looked at Gaussian and things like that, but when you plug this lower bound, it works beautifully, which means like if the class is well separated, if a lower bound also is not that bad. So now here, what is important is that what are sigma A's, sigma B's, and mu1, mu2. So now here, as I said, is distribution, right? Now we look at the mean and the variance of the underlying responses to the neurons. In other words, it says that I do not even need high quality training data. All I need is some sense of the moments of the outputs of individual components. That gives us a very good setting. That is, if you have reasonable proxy of the data, it should work, and that is what it is showing up here. Okay, so this is just the experiment slide on how wide discriminant filters, what we see, and we see that it exists, and maybe I'll just skip this slide in interest of time. So our solution also, but here's the point to be noted, this slide is that, for pruning, it seems, for example, one baseline can be random pruning, randomly throw away things. That's a valid baseline, right? But now, often it is known that sometimes it works, sometimes it doesn't work. Why? So the layer-wise, in each layer, things behave differently. So now I cannot have the same randomized pruning strategy everywhere. Now we could, because of this, our discriminative filter hypothesis, we will be able to compute a fraction, like fraction of the tau is a fraction of this, and that gives us a very good way to check that in this filter, is it how much should I prune? Is randomized. So this is what we call as degree of difficulty of pruning in a particular layer, what we call LDIF score, right? It resonates. It talks to the problem of why sometimes random pruning works and sometimes it doesn't. Yes.
Since you're mentioning all this, that you can identify discriminative filters and so on, right? Can you comment something on the explainability, because I think that might be related to that, hopefully.
Yeah. So okay, good question. So explainability means many things to many people, but here that is the same ability now, which will help me do model unlearning as well. So indeed, so there is differential treatment of differential response to each of the structures has more play, which goes beyond pruning. Explainability, of course, means a big things, but interpretability for sure. All right. Yeah. So maybe that's precisely my point as well, our point as well. But yeah. So now, so this is the first thing on TVS prune. So we made assumption that things are Gaussian, right? But now the question is that is there a better solution for this? So now here comes this question as Chetan asked. So now can you make it more fine instead of this TV distance? Of course, we have because we resort to this Gaussian assumption and all that, right? Can you make it more specific? Find components which are most discriminative. So to do that, I need a definition of discriminativity, right? Now there is a very famous, classical result that. So this R star is basically the Bayes error, as it's called. Bayes error is to those of you who have taken a course in pattern recognition, the first thing is taught. Bayes error is the classifier which can best distinguish between two distributions, right? Between two classes, let's say. So this is no classifier can beat this error rate. So that is a relationship. The R star is the Bayes error rate with TV distance, right? Right. So of course the NP hardness that thing remains, but opens my mind to some other thing. Is that I see. So Bayes error rate means TV distance got something called the Bayes error rate. Then what I can do is my vanilla thing can be if I take a neuron or a structure, train a network on that, a classifier on that, and whatever the accuracy is, I can use that as a proxy. I don't need to make these assumptions with Gaussian and things like that, right? So just like the previous thing, we went ahead and did all of this, but then what we contribute to the basic fundamental theory of machine learning as well, which goes beyond this, is that we think, like, here is a new contribution of ours where we thinking like the classification cases, but we are happy to say that we are able to compute a lower bound using a variety of functions which are called witness functions. So I can, and these f's can be whatever, you can choose from a large variety of design functions, and which will be able to give you a large variety of different kinds of bounds on TV distance, right? So one of the examples of this is, a special case of this is the so-called Fisher discriminant. Anyway, so this is a little bit theoretical, however, okay, sorry for this slide. The point about this is not this theorem. The point about this also requires estimation of moments and means and the variance, as we saw. It doesn't have to be Gaussians and all that. Now, what's the problem with that? The problem is that it depends on the number of samples. So two observations. First observation is that what we find surprisingly, not always though, that in CIFAR10, for example, it's a small data set, it's a small number of classes. Classes are reasonably well separated. In a very small number of samples, the mean variances does a great job. But soon as the sample size, soon as the class size increases, like CIFAR100, we start requiring more samples, right? So one needs to have an articulation of this, that can you make this bound a little robust, so that we can also attribute to that, and that's where this theorem is speaking to that point. So let me speak to the point about complex interconnections. So it's a complex interconnection. So all of you, so complex interconnections is this particular problem. Suddenly this resonance has this, that suddenly you skip a layer, right? Skip connections. Why were they introduced? They were introduced to handle the problem of vanishing gradients. But this was not there. If those skip connections were not there, that's a standard network. It was working well. But however, it became difficult to train as the layers increase. Why? Because the gradients were vanishing. Now to solve the vanishing gradient problem, the skip connections were introduced. And this is, resonance is that example where they did this, and it was amazing. However, now here comes the bad part of it. Now I want to prune models. Here we get stuck. Why? It must, now when you are doing back propagation now, you see this entire thing as because of the skip connections, my data flow got completely messed up, and hence it requires sort of structured pruning requires new thinking for this perspective. And now, so when we see in literature, maybe I should use this slide, I guess. So basically, this, I'm sorry it's not showing up. There's some, there are pluses and all that, right? So pluses are the skip connections, right? Now the data flow in this, so in these cases there are some neurons which have the connections. For them, the pluses are all have the skip connections, right? And some neurons don't. So there are many layers for which this pluses, the connected components, most algorithms will not even touch it. Why? Because they're unable to take a call that if I remove it, what is going to happen? I do not know how the gradients will change. So what they do is avoid it. Fine. But the problem is we profile this, and I see that 66%, like 2/3 of the inference time goes into these things. And they could not do it because the mathematics of it is not allowing us. So how do you go about doing things, right? So now, so basically now most of this algorithm goes like this. What you do is, here's a filter you want to remove, great, or you want to, some structure you want to remove, fine. So you compute what is known as an importance or saliency. Now you sort the things out by saliency and say that, okay, the most salient ones you keep and the rest you don't keep. That's basically the hallmark, right? In the same way now, so now because there's a skip connection, right? Now in a feed-forward network, it makes perfect sense I can treat each neurons individually. But in this group thing, I cannot treat them individually. I treat them in groups. And now suppose there's an element, let's say neuron 2 in both groups. Maybe one group here, there's neuron 2 somewhere up there, right? And it's also there in this group. Now we see, now if I do this individual approach, this neuron 2 is important and is not. So what do I do? Should I keep neuron 2 or not? Because it's in two groups, right? In one group saying I need to keep it, another group saying not. And that is the thing, we tried many measures and see all of them has this conflict. So obviously this is not the way to think about it, and most of the thinking is based on feed-forward networks. So now the interesting thing is, and here Tanay invented this new thing that he invented a mapping where this feed-forward network, the skip connections can be thought about as a you can map it, which is called the DFC, like a data flow couple channels. And so that you can track the data flow in what way, and that is the way to go about computing saliency. And now this works, since I'm putting on a slide and got accepted paper, it works very well. This code is also available. Okay, so I think I'm almost out of time, so maybe I should show. Okay, this is one slide I need to show. So as I said in the beginning, right, that okay, pruning is there. A lot of good research has happened and exciting and interesting, but sometimes we just throw away parameters does not end up in energy saving. So one better proxy than simple parameter reduction is flop reduction, right? And now if you see now, the idea is that this DFPC shows remarkable flop reduction. I mean, this has to be improved to much more, but as given the state of the art, it's a remarkable improvement, right? So I think, so basically it also says that we need new measures also on evaluating the accuracy of our pruning and things like that. But now coming to model unlearning, that's what the last thing is, and I'll take a couple of minutes. So as we said, right, so model unlearning definition is a model is trained from scratch from a set of from a data set without the target examples. Then the model is said to have learned it's said to have unlearned the target examples. That's the target thing says. Scarlett Johansson thing is forgotten, right? Now the question is, can I do this efficiently? This kind of thing is not efficient. I cannot return everything, right? So now, I mean, this, as you can see, is the beginning work happening, lots of the excitement, influence functions and things like that. So now what we can do is now, because of our discriminative filters, we now know which filters react differentially to dogs, cats, etc., right? Now you can use it to control that. And now here is our one slide result. So this blue line is the accuracy result, like the original accuracy result. So blue class is, for example, here it is, what is it? Yeah. So you want to forget class 0, let us say, right? So this is the accuracy of the blue class. This is class 0, and this is the rest, 1 to 9. Right? Now we run this algorithm, that is the discriminative filters, that is throw away discriminative filters for class 0. You see, accuracy on this class, the remaining class remains roughly the same. But the blue class has shrunk this much. Right? Just by identifying discriminative filters. So this shows the power of this, and this also will, I'm sure this will also shed new light on many other problems where interpretability is demanded, Anyway, I think I'm out of time, 10:30. So thanks for listening. It's been wonderful talking to you here. Sorry I couldn't finish my slides, but I think that's fine. Thank you.